Hello MYP5, we are on page number 518 and we are looking at the exponential functions. Exponential functions is like exponential graphs. Okay, and general shape of our exponential function is looking like this. So on page 519, that's our reference page. Every exponential function, you will see your graph is either increasing or in another case it is decreasing. You will see your graph will go closer and closer to the x-axis, but it will not touch the x-axis, right? The equation for this graph is y is equals to a to the power of x, and you will normally see it's crossing the y-axis at 1. Keep in mind, it does not have any x-intercept. So it will only have a y-intercept. Your graph will go closer and closer to the x-axis, but it will not touch the x-axis. Okay, so your graph is starting from the left and climbing on the right hand side. It's only the case when your value for a is greater than 1. Okay, now there's another case. Your graph is starting from the left. We know that we always read things from the left hand side. It's starting from the left and it is going closer and closer to the x-axis, right? In those cases, your value of a will be between 0 and 1. That means that's a fraction value. There you go. And it will again go closer and closer to the x-axis. It will not touch the x-axis. So that is the x-axis in this case is the asymptote. Here again, the x-axis in this case is the asymptote, right? So general equation, your any exponential graph will be in the form of y is equals to a times b to the power of x, right? In this case, the number that is associated with b is always the initial value, right? The starting value, the value at the beginning. The x is my independent variable. The y will be my dependent variable, and b is my growth or decay rate. This b will be in terms of the rate, right? Keep in mind, we will always use the value of the rate in decimal. Okay, now let's get back to the textbook. You will see there's few explorations explaining that, and we are going to look at example 1 on page number 522. Okay, there are 128 players in a tennis tournament. Half of the players are eliminated after each round. Write a table of values and the function of the number of players after x round. Okay, you'll see before any round would happen, we had 128 players. And then half of the players, the main word here is the half of the players. That means my decay rate, in this case we can say it's a decay rate because the number is going small, so the decay rate is gonna be half, right? And then 128, that's my value for a times half to the power of 1. And then in the second round, half to the power of 2. You will be left with 32 players. In the third round, half to the power of 3. The value of x is 3, same, and then so on. In the seventh round, you will see there's only one player left, right, in the seventh round. Okay, part B of the question. Determine the number of rounds needed to declare the winner. Winner will be only that person when there's only one person left. So only one person is left in the seventh round. So seventh round is going to have the winner. Okay, right, so we're going to look at more examples, right? Okay, let's look at that. Exponential growth and exponential decay. Now we will modify our formula a bit. For exponential growth, that means the number is increasing. So y is equals to a times b. This is my entire b. So entire b I'll be replacing with 1 plus r. R is my rate, okay, to the power of x. Exponential decay, this is my formula for exponential decay. So decay, the number is going less. Growth, the number is coming up. That's why we have a plus in this and a minus in that. Okay, you'll better understand more in the next example that we are looking at. Okay, let us look at example 2 on page number 524. It says the population in a town was estimated to be 38,000 in 2015. Since then, the population has increased each year by approximately 2.4%. Keep in mind this is given in terms of percentage, but in the formula we will be changing that to decimal. Okay, determine the growth factor by B of the population in the town. Let's look at the first one again. Determine the growth factor B of the population. Alright, you all know your general formula for the growth is A times B to the power of X, and we know that the B in the last formula I told you will be replacing with 1 plus R, and R is the rate in decimal. So my value for B is entire this value 1 plus R. 1 plus, that was my right, 2.4% in decimal is that, so 1 plus 2.4%. That's my value for B that I have, or you can have B is equals to 1.024. Right? Okay, let's look at part B of the question. It says write a function to model the further population growth. We have to write the formula. Again, my general formula is A times B to the power of X, and A, I've already told you, is always the initial value, the starting value. You already had 38,000 people there, and B was 1 plus 0.24 to the power of X. I'll simplify that. 38,000 times 1.024 to the power of X. Okay, let us look at part C. Part C says, use your function to estimate the population to the nearest 100 in 2030. Now, we at the moment have the function from 2015 and it's talking about 2030. So, let's see how many years. 2030 minus 2015, we have 15 years. So, my value for X would be 15. That means in place of X, I'll be substituting 15 in my formula. 38,000 times 1.04 to the power of 15. I'll have 54,200 as my solution. Right? 54,200 people. Okay, let's look at one more example. Let's look at example number 3. Sarah bought a car for 15,000. Its value depreciates. Okay, now we can see this is a case of decay. The price is going down. Its value depreciates, loses the value by approximately 15% every year. 15%, that's my rate. Okay, find the depreciation decay factor. Keep in mind, in the decay factor, we are going to be having 1 minus, okay. Once again, my general formula is A times B to the power of X. Y is equals to A times B. The decay factor will be 1 minus R to the power of X. So, my B will be 1 minus R. 1 minus 0.15. That was given in the question in terms of percentage. But keep in mind, we will always use decimal. So, 1 minus 0.5 is 0.85. Okay. Let's look at part B. Write a function to model the future value of the car. Once again, Y is equals to A times B to the power of X, and A is always the initial value. In this case, the value that I bought the car for times 0.85 to the power of X, and 15,000 times 0.85 to the power of X would be my answer. Right? Okay, let's look at C. Use your function to estimate the value of Sarah's car after 3 years. After 3 years to the nearest dollar. Okay, so that means my value of X is 3. In place of X, I'll be substituting 3. After 3 years, my value of the car will be 9,212. So that was on exponential function. Thank you.